This course describes routing policies through 3 common tools: Roule-policy, IP-prefix list, and filter policy. First, let's talk about the Roule-policy tool. To understand the Roule-policy tool, we first need to understand the background. On the network shown in this figure, there are 3 routers, R1, R2, and R3. To communicate with each other, R1 and R2 use RIP, and R2 and R3 use OSPF. The routing table of R2 contains both RIP routes and OSPF routes. By default, R2 does not import learned RIP routes to OSPF, and nor does it import learned OSPF routes to RIP. To import RIP routes to OSPF, perform the following operations on R2. Enter the OSPF view from the system view of R2 and run the import route RIP command. You can specify the cost parameter in the command to configure a cost for the RIP routes to be imported to OSPF. After the preceding operations are performed, R2 imports all learned RIP routes to OSPF. What if we want to import only some RIP routes to OSPF, or set different costs for the RIP routes to be imported to OSPF? We can use the Roule-policy command in this case. A Roule-policy contains a list of 1 or more nodes. When deploying route re-advisement, you can associate it with a Roule-policy to filter routes or set route attributes. Let's look at the Roule-policy tool in more detail using the Roule-policy RP as an example. A Roule-policy contains 1 or more lines, each of which is a node. Each node has an index, and nodes are arranged in ascending order of their indexes. Each node can have condition and action clauses configured. The action clause is executed only if a route matches the condition clauses of a node. Condition clauses start with the if-match keyword, and action clauses start with the apply keyword. The system matches a route against the Roule-policy node by node in sequence. Specifically, if the route does not match all the if-match clauses of a node, the system further matches the route against the next node. If the route matches the current node, the system does not match the route against the next node. To create a Roule-policy, run the Roule-policy command in the system view. Then, enter the Roule-policy name, specify the permit or deny mode, and set a node ID if the permit mode is specified for a node and a route matches the if-match clauses of the node. The apply clause of this node is applied to the route, and the route is no longer matched against the next node. If the route does not match the if-match clauses of the node, the route is further matched against the next node. If the deny mode is specified for a node and the route matches all the if-match clauses of a node, the apply clause of this node is not applied to the route and no further matching is performed against the next node. If the route does not match the if-match clauses of the node, the route is further matched against the next node. Now, we can configure if-match and apply clauses for the node that is displayed. You can configure an ACL-based if-match clause to filter routes. On Huawei routers, ACLs specified in route policies can be used to filter routes based only on the network address. Alternatively, you can configure an if-match clause based on other information carried in the route, such as the cost or outbound interface. A node can have 1 or more if-match clauses, or no if-match clauses at all. If a node does not have any if-match clauses, all routes match the node. If a node has multiple if-match clauses, the relationship between these if-match clauses is AND, meaning that a route matches the node only when it matches all the if-match clauses of the node. The if-match ACL and if-match prefix commands are mutually exclusive. The relationship between the if-match clause configured using the if-match route type command and the one configured using the if-match interface command is OR. After the preceding configurations are complete, we can configure an apply clause. Apply clauses can be used to change information carried in the route, such as the route cost, OSPF cost type, or next hop IP address. The topology contains two routers, R1 and R2. Both routers run OSPF. R1 has 3 directly connected interfaces. By default, R2 cannot learn the 3 direct routes from R1. To import the 3 routes to OSPF, run the import route direct command in the OSPF view on R1. After the command is run, the directed routes on all interfaces that are up are imported to OSPF. Suppose it is required that only one of the routes be imported to OSPF and its cost be set to 20. To meet the requirement, we can use the following method through a route policy. First, create an ACL named 2000 and configure a rule for it to match the directed route to be imported. Suppose we need to import the route 172.16.1.0/24. You need to set the network address to 172.16.1.0 and the wildcard mask to 0.0.0.0. Second, create a route policy and configure an if-match clause to invoke the ACL 2000. Finally, run the import route directed route policy RP command in the OSPF view on R1 to import the desired route to OSPF. Here is another example. The topology contains 3 routers, R1, R2, and R3. They all run OSPF. R3 is connected to a terminal network, and 2 core switches are connected to a server cluster, which consists of 2 network segments. The switches function as the gateways of the server cluster. A static route is configured for R1 and R2 to reach their connected switch. In this case, R1 and R2 can access the server cluster, but R3 cannot. R3 resides in an OSPF area and cannot communicate with the switches. As a result, the terminal network connected to R3 cannot access the server cluster. To allow the terminal network to access the server cluster, deploy route re-advisement on R1 and R2. Suppose it is required that the data traffic of the terminal network accessing the network segment 10.0.1.0/24 flow through only R1, and that the data traffic of the terminal network accessing the network segment 10.0.2.0/24 flow through only R2. To meet the requirement, we can use the route policy solution. Specifically on R1, configure 2 static routes to the network segments of the server cluster. In this way, even if R2 fails, the terminal network can still access the server cluster through R1, which provides network redundancy. Then, in the system view on R1, run the import static command to import the static routes to OSPF. Similarly, perform the corresponding configurations on R2 to meet the traffic forwarding path requirement. We can configure a two-node route policy on R1. The first node is used to match the route 10.0.1.0/24 and set a route cost 10 in this example. The other node is used to match the route 10.0.2.0/24 and set a larger route cost 20 in this example. Of R2, when configuring nodes for the route policy, set the cost of the route 10.0.1.0/24 to 20 and the cost of the route 10.0.2.0/24 to 10. In this way, the data traffic of the terminal network accessing the network segment 10.0.1.0/24 flows through R1, and the data traffic of the terminal network accessing the network segment 10.0.2.0/24 flows through R2. This slide lists the configurations on R1. This slide lists the configurations on R2. Now, let's move on to the second chapter to talk about the IP-prefix list tool. As we mentioned, on Huawei routers, ACLs specified in route policies can be used to filter routes based only on the network address rather than on the mask. In most cases, the wildcard mask in such ACLs is set to 0.0.0.0. Using ACLs to filter routes has a disadvantage. Assume that R2 learns two routes 192.168.0.0/16 and 192.168.0.0/24 through RIP. The two routes have the same network address but different network prefix. It is required that the route 192.168.0.0/24 be filtered out during the RIP route import to OSPF. To meet the requirement, create a route policy and invoke it when configuring RIP route import to OSPF. If we use an ACL to configure a filtering criterion for the route policy, the route 192.168.0.0/24 cannot be filtered out because the ACL cannot differentiate the two routes. Let's use an example to describe an IP prefix list in detail. To configure an IP prefix list, run the IP-prefix command in the system view. This example shows the configuration of an IP prefix list named HCMP. The index of the current entry in the IP prefix list is 10, and the entry works in permit mode. The IP prefix list matches the route with a network address of 192.168.4.0 and a mask length of 24. Following the mask length, two parameters, greater equal and less equal, are optional. The two parameters are used to define a mask length range. For example, if the two parameters are not specified in this example, the configuration of the command matches only the routes whose network address begins with 192.168 and whose mask length is 16. If the two parameters are specified and their values are both 24, the configuration matches the routes with network address of 192.168.0.0 and mask length of 24. If greater equal is specified but less equal is not, the mask length range is from the greater equal value to 32. If less equal is specified, but greater equal is not, the mask length range is from 16 to 24 in this case. If an IP prefix list has multiple entries, the system matches routes against the IP prefix list entry by entry in ascending order of entry indexes. If a route matches one entry, the system considers that the route matches the IP prefix list without further matching the route against other entries. Here are some examples of IP prefix lists. The first one matches the route 192.168.1.0/24. The second one matches the default route. The third one matches all host routes. The last one matches all routes. In this example, it is required that the minimum configuration be used to match all the routes listed here. To meet the requirement, we can configure one entry for an IP prefix list. To do so, we need to first convert the dotted decimal notations of the routes to their binary counterparts. Then, we need to compare the binary values to determine the number of bits. Starting from the most significant that are the same among the binary values, in this example, the number is 22, meaning that the network address of the routes to be matched is 192.168.4.0. Because the mask length of all routes listed in this example are both 24, we need to use greater equal and less equal parameters and set their values to 24. In this example, R2 learns two routes, 192.168.0.0/16 and 192.168.0.0/24 from R1 through RIP. It is required that only the route 192.168.0.0/16 be imported to OSPF. To meet the requirement, the configurations listed in this slide can be performed. Finally, let's talk about the filter policy tool. The filter policy tool is mainly used to control route sending and receiving. However, the filter policy tool can be used to filter routes, but not link state advertisements, LSAs. LSAs are messages exchanged between OSPF routers. In this example, the routes 192.168.1.0/24, 192.168.2.0/24, and 192.168.3.0/24 of three network segments connected to R1 are advised to the RIP domain. After learning the three routes from R1, R2 sent them, and the routes of the network segment between R1 and R2 to R3, it is required that a filter policy be configured to prevent R2 from sending the route 192.168.3.0/24 to R3. To meet the requirement, we can first run the IP prefix 1 192.168.3.0 command on R2 to prevent the route 192.168.3.0/24 from being advised. Then run the IP prefix 1 permit 0.0.0.0 less equal 32 command to allow other routes to be advertised. Finally, run the filter policy command in the RIP view to apply the filter policy to R2's interface that is connected to R3. Here is an example of filtering the OSPF routes to be received. Three routers, R1, R2, and R3, reside in the same area, area 0. R1 advertises a subnet route 1.1.1.0/24, and R2 and R3 learn the route. If we need to prevent this subnet route from being added to the routing table of R2, we can perform the configurations shown in this slide. Although the filter policy import command is run, the LSA of the subnet route can still be added to the link state database LSDB of R2. In this case, R3 can calculate the route 1.1.1.0/24 according to the LSA. Specifically, the filter policy on R2 does not affect R3. In this example, R1 and R3 reside in different areas. If the preceding filter policy is configured on R2, R2 does not flood the Type 3 LSA carrying the route information in area 0 to area 1. As a result, the route 1.1.1.0/24 does not exist in the routing table of R3. That's all for today. Thanks for listening.